All right, we're recording. So what if we wanted to find the slope of the tangent line of this function at these 5 points, or even more? What if we want to do it at 20 points? Based on our current knowledge, what we have to do is, like the warm-up, you'd have to set up a difference quotient, do that in some kind of algebraic manipulation so that you can evaluate the limit at h equals 0, which it's possible to do. We've done several of them. But you'd have to do it every time, and it might not be your preference to do that. It is a lot of work for just the slope of a tangent line. So it'd be nice if we could do this computation once and then be able to just plug in 1, 2, 3, 4, 5 into our final result and just be able to immediately have the slope of the tangent. We're getting there. So what I'd like you guys to do, one more time, can you guys, like the warm-up, set up and evaluate the difference quotient for x equals 1 and do our algebraic manipulation, plug it at h equals 0, and we'll get the slope of the tangent line when x is equal to 1. And then we're going to imagine, well, what if we did this not a specific x value, but just did that calculation in general for any x value? What would kind of come out? And I will do B with you, but I'd like you guys to do A so we have something to kind of parallel. So this is where, as a teacher, I'm going to resist the urge to just do it for you right now. I'll have a sip of coffee and wait a second. And you guys try setting it up. We've done many of these now. 2 more in the warm-up. And I'll come along for the ride in a second. Mm-hmm.
So in this one, we don't have a line here. Would you still minus 2 here?
Yeah, because you can. I did this on the warm up, but you can just plug in 4 and find the y value.
Oh, in this way.
Yeah. Okay. All right. I'm going to zoom in a little bit because my fine motor skills suck. And let's go. So the function is the function is 4x squared. So f at 1 plus h would be 4 times 1 plus h squared. F at 1, when you plug in 1, you get 4 for the function. All over h. Very similar to the first warm-up question. When we expand and simplify, the constant terms should go away on top. We should be able to factor what's left. So I will do that with you guys. So 4, 1 plus h squared is 1 plus 2h plus h squared. Going to keep mentioning, some students come in with the misconception, don't write this down, that a plus b squared equals a squared plus b squared. That's not true. There's the cross term 2ab. So this was a grade 10 thing. You guys learned in grade 10, perfect square trinomials. So I'm just making use of that fact now. But yeah, just don't do 1 plus h squared. Erase, 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 erase. All right, so I've done this problem like 25 times, but even if I hadn't, I can look ahead and see, I'm getting 4, and I'll be subtracting 4, which is good because I want the constant terms to go away. And we get the limit as h approaches 0. So we get 2h plus h squared over h, or h squared plus 2h. I'm not your dad. Put them in whatever order you want. And then if you guys are okay with this, because there's just an h in everything, I'm just going to divide out the h from everything, tick down the powers of h from every single term, and I'll be left with the limit as h approaches 0 of 2 plus h. I can do that here because every single term has an h. there's nothing wrong with plugging in 0 here. Did I do something wrong? I did do something wrong. Well, yeah, you do multiply. Why'd you guys let me do 3 other steps? Bunch of sheep just letting me. Okay, so this is a good talking point because I am a human being and I make mistakes all the time. Sometimes you guys think it's not okay to make mistakes. It's totally reasonable to make mistakes. I make them all the time. I made one here. I did not multiply everything by 4, so it's an easy fix. But yeah, we should multiply everything by 4. So that should be 8h plus 4h squared. But like, I am more than happy to be corrected. If you guys notice I make a mistake, just let me know. So that would change this one to be 8h. I was actually starting to figure out something was wrong because I'm like, this isn't what I got when I did my note earlier. That's looking better. 8 plus 4h. Plus 4h. Looking better? All right, you guys gonna let me know if I make a mistake? Probably not. But all right, let's continue. Nothing wrong here with plugging in h equals 0. So we have found the slope of the tangent line to this function at x equals 1 is exactly 8. Now, if we want to do this again for 2, 3, 4, and 5, with our current tools, we would just have to redo the whole thing. But I'm going to propose this to you guys. What if, instead of plugging in a specific value for x, what if we just left x as x and did a general calculation for the slope of the tangent line? We now have a nice parallel at the left, excuse me. I know left and right. Assuming I don't make a mistake again. But yeah, let's dive in here and let's repeat the drill, but with just a general x value. So here we go. So at the limit as h approaches 0. So our function is 4x squared. So f at x plus h would be 4 times x plus h squared. Where there's an x, put in x plus h. And then this time, instead of subtracting a specific y value, we're just going to be subtracting the function itself, which is 4x squared, all over h. Nothing really has changed. We're going to proceed as normal. We're going to expand. We're going to simplify. We're going to see if we can get this to a point where we can just plug in h equals 0. So I usually like to say at this point, if you guys recall back in grade 10, whoever your math teacher was, you probably spent several days just expanding and simplifying and doing FOIL over and over and over again. Well, the point was like so that you could get to calculus, and expanding something like this doesn't require too much brain power. I'm just applying my perfect square trinomial pattern. I'll have x squared and h squared and double the cross product, 2 times x times h. Minus 4x squared all over h. Same process, right? Just a little more variables in there. Let's distribute the 4 this time. So we'll have 4x squared plus 8xh plus 4h squared minus 4x squared over h. Guys, the same thing that happens all the time is happening again. Everything that doesn't have an h in it is going to go away on the top. 4x squared minus 4x squared is equal to 0. We're left with the limit as h approaches 0 of 8 times x times h plus 4h squared over h. Can't plug in 0 yet because everything on top has an h in it. We would get 0 plus 0 over 0. That's 0 over 0. That's bad. But strategy from yesterday, what if we factor? And if you guys are okay, just to manage my space here, 8xh has an h in it, 4h squared has an h in it, and those will divide with the h on the bottom. So we'll get the limit as h approaches 0 of 8x plus 4h. There's nothing wrong with plugging in h equals 0 here, so we're going to do it. And we get 8x. So what we've done is very powerful. What we have just done is we've shown for this function 4x squared, to get the slope of the tangent line, at any point, what you do is you just multiply that x value by 8. So you want to find the slope of the tangent line at x equals 1. 8 times 1 is 8. And that's what we got over here, right? We got 8. But now you want the slope of the tangent line for 2, for 3, for 4, for 5, for anything. We don't have to do a whole difference quotient again. We can just use this rule. This rule says the slope of the tangent line for this function at any x value is just 8 times the x value. So, might seem pretty trivial, but let's just do this down below where I've given us some space. If I could go over here, yes I can. Dehance, dehance, dehance. All right, yeah, this is good. No more difference quotient. Slope of the tangent line at x equals 2 is just 8 times 2. I got a lot of space for this. I don't know why. X equals 3, 8 times 3. I know you guys know your 8 times tables, maybe. 8 times 4, 32. X equals 5. 8 times 5 is 40. Wasn't that better? We didn't have to do the difference quotient every time. We did it one time and got a general rule, and now we can find the slope of the tangent line all the live long day at any x value we want. This operation we did, this exercise on the right, is so useful. We give it a special name. And this is officially the part of the course where we introduce the derivative. You guys have found your first derivative. The derivative of 4x squared is equal to 8x. It's an expression that gives you the slope of the tangent line, the instantaneous rate of change at any x value. So before we start defining some stuff, anything you guys want to chat about what we did? Hopefully the last several days was just a nice progression and build up to this point. All right, so let me tell you what we're doing today, tomorrow, and what we want to move towards. So we've got some definitions, some new terminology to talk about, and we're going to find derivatives of various functions today and tomorrow by using this definition and doing this exercise for a variety of functions, with the goal in mind to start seeing if we can develop some rules where I can just look at a function like 4x squared. Where's my function? I can look at a function like 4x squared and apply some rules for finding derivatives and be able to find the derivative in a matter of seconds instead of having to set up the difference quotient. We're going to get there, but we are going to do a few more exercises like this. It's where we're going. All right, so let's continue. All right, so the derivative of a function f of x with respect to x is, first of all, a function itself. So we just did the function, quadratic function 4x squared. And when we found this derivative, and maybe you guys could actually add this to your note. I'm just improvising here. What we did was we found the derivative of that function. It's read f prime of x. That operation we did was finding our first derivative. So let me head back here. All right, so the derivative of a function is another function where, and this is where we're popping in our derivative. Here we go. F prime of x is equal to the limit as h approaches 0 of f at x plus h minus f at x all divided by h. And we now know exactly where this comes from. This is our difference quotient. The limit as h approaches 0 just means we're putting our 2 points really close together. And then instead of a specific x value, we're now just doing a general x value. But it just comes from the slope of secants and bringing the points closer together. So yeah, again, hopefully the last few days was a nice progression. I have 2 key ideas here. The first is this. I'll just write it out instead of typing it out. The first is that the derivative of a function is also a function. So we found the derivative of 4x squared, and we got 8x. It was a linear function. And then I've been mentioning this many times, but let's just jot it down. I should also note too, I have a note here to say this. If you want to know how to read this, we read it as f prime of x. Just like a function notation. It's f of x, but that little tick we read as f prime. So f prime of x. All right, so f prime of x gives the instantaneous rate of change. And in brackets, I'll just add the tangent slope, same thing, to the function f of x at any value of x. So don't lose sight of what this derivative means. The whole build up to this point has been it's the slope of a tangent line. It's instantaneous rate of change. All right. F prime of x is new tech for you guys. It's a new notation. It's what we're gonna use for the derivative of x. There is many other notations as well. So in the textbook practice we draw from, you might see any of the following notation for the derivative, or any other resources you guys look at or check out. So we have f prime x, but if the original function was given to you as like y equals 4x squared, which might still happen, then we would say the derivative would be y prime. Or this notation is called Leibniz notation. You might see dy by dx. This is kind of a riff on slope. You guys know how slope is rise over run, delta y over delta x, kind of a similar thing there. Or you might see d by dx of f of x. I don't really prefer this notation too much, but they all just mean the derivative of a function. All right, you guys still doing okay? At this point, we're just going to find some derivatives together. And when we find a derivative using the difference quotient, what we're doing is we're finding the derivative from first principles. Because later we'll have some rules to find derivatives just like that. But to start off, we're using the definition. We're finding, when you see, if it says find a derivative using from first principles, it just means set up your difference quotient. So I'm going to do this one with you guys. And then, yeah, as I said, our goal is just to get some practice finding derivatives. So here we go. Let's find the derivative of the radical function from first principles. So we're going to set up the definition of the derivative, f prime of x. It's the limits as h approaches 0 of f at x plus h minus f at x all over h. And then we'll plug in the stuff that's specific to our function here. So we have the limit as h approaches 0. So f at x is root x. F at x plus h would therefore be the root of x plus h. And then we'll subtract f at x, which is root x, all divided by h. When you guys are doing practice, I would probably suggest writing the definition out, at least for a while. But eventually, you can just start plugging in. Again, I'm not your dad. It's your practice. You do what you want. Another question I often get about this time is like, do we need to keep writing the limit in as we go? Like if I flip back to this one here, it's like limit as h approaches 0 and over and over and over and over again. And the answer is yes, we need to keep writing in that limit until the point where we directly substitute h equals 0 into it. And I'm going to erase this in a second. But just putting an arrow like this, that's not that's cheating. Don't do that either. Or don't put like vertical ticks like that. No, we do have to write in the limit. Okay, please and thank you. Don't be cheeky like that. All right, so if it's we're going to be using the same skills from the last several days. It'd be nice if you could just plug in h equals 0, but look what happens. We would get root x minus root x, which is 0. We get 0 over 0, not good. But we have a strategy, even though this is a bit more of a complex scenario because we have two variables, x and h, we have a strategy that helps us evaluate limits like this. We can rationalize. So let's multiply by the conjugate of what's on top there, root x plus h minus root x, plus x, plus root x, over the root of x plus h plus root x. You guys basically did the same thing in the warm-up. You did this literal question in the warm-up. It's just instead of x, you used a number, I think we used 4. But I'm doing this one with you guys. So let's just continue. So hopefully we've established that we have this pattern. So root x plus h times root x plus h is just x plus h. And then we'll have minus root x times positive root x, which is just minus x. That's how square roots work. The cross terms will add to 0, so that's the top. And on the bottom, h times all the other stuff. And you guys are still looking for those common themes. You always want the h on the bottom to divide out, which means you expect all the stuff that doesn't have an h on the top to kind of cancel it to 0, add, subtract to 0. And that does happen here. Now we've done a few of these now, so if you're recognizing the simplifications you can do, for example, I might do this here. So if you guys just want to follow along and make sure you're good with this, like I can see I have x minus x, that's 0. And then I can also see, well, I'll have h over h, and h over h is equal to 1. So I can maybe save a step, because we are doing lots of writing here, and maybe I can do those two things at once. X minus x is 0, h over h is equal to 1, and I'll be left with this, 1 over the root of x plus h plus root x. Again, because h over h is equal to 1. So we have it in video if you want to go back and rewatch what I did there. But it's okay to do that in one step if you're comfortable. It's okay to do that in 2 steps if you need to, whatever you need to do to feel comfortable. Nothing wrong now at this point, everybody, with plugging in h equals 0. That is okay for us to do. At this point, we can drop the limit. So we have 1 over, I don't like how I wrote that, equals 1 over the root of x plus 0 plus root x. You could have just wrote 1 over root x plus 1 plus root x if you wanted to. I'm showing extra steps because I have the space here. That's just 1 over root x plus root x again. And root x plus root x is equal to 2 root x. We did it. The derivative of the radical function, root x, is equal to 1 divided by 2 root x. We can even check that this works out. We did this in the warm-up, right? Did we do this one in the warm-up? Did we do? I closed it down. But did we not do root x at x equals 4 in the warm-up?
Yeah.
We did that, right? And we got, we got 1 over 4, right, in the warm-up?
Yeah.
Do we get 1 over 4 here for the same thing? Yeah, you do. You plug in 4. The root of 4 is 2. 2 times 2 is 4. You get 1 over 4. Everything checks out. But now, if we revisited the warm-up and said, see how the tangent line changes at 5, 6, 7, 8, hundreds of values, you now have a nice tidy expression you can just plug your x value into. So we've done a polynomial. We've done a radical function. Anything you guys want to chat about so far? We are testing your algebra skills for sure. So that's why in grade 9. Now, if you can imagine a grade 9 student saying, why do we have to do this? Why do we have to practice distributive law, stuff like that? We can't just say to our grade 9s, well, you're going to need this in calculus. But now you guys are here and you need all those skills. So hopefully, if you were somebody who pestered your teachers and said, why do we have to do this? Well, hopefully you're, appreciative now of all the practice that they gave you, because we need it. All right, let's do another one. We've done a quadratic. Let's do a cubic from first principles. So I'll walk through this one with you guys, at least to start. I'll let you guys finish it off. And then we'll kind of move into releasing the responsibility onto you guys in terms of practicing. And just as a heads up before we're going, tomorrow I don't plan on teaching anything new. We'll just have a day to practice working on derivatives. So if you find we do a few examples and we're bumping up against 950, it's okay, because we're just at this point, for the next 2 hours of class time, basically, we're just practicing our derivatives. All right, let's set this up. So f prime x is equal to the limit as h approaches 0. So I'm writing out the definition of the derivative. And now I'll plug in my function. So the limit as h approaches 0, x plus h cubed. And my function is x cubed plus 1. So f at x plus h will be x plus h cubed plus 1. And I will subtract. And then f of x, we need to be careful here. F of x is equal, I'm subtracting all of f of x. So I'm subtracting all of x cubed plus 1 divided by h. I've taught grade 9 recently, and when we do adding and subtracting polynomials, I can remember being asked the question, why are we doing this? Why are you showing us this stuff? Why are you giving us these tips and tricks? Because now here, you need to make sure you're subtracting all this polynomial. You'll be subtracting x cubed, and you'll be subtracting 1. If you didn't include the brackets here, then you would have a sign error. Your 1s would not cancel out, and you'd have a problem finding the derivative. So a lot of algebra skills, even from grade 9, grade 10, start to come together. We need them all in calculus. So at this point, it's just the usual expand, simplify. I'll do this one with you guys because I believe, if I recall from last week, you guys have seen Pascal's triangle, but didn't exactly get to how it helps you expand. So I'll help you with the expanding here. And then I pinky swear promise not to have you guys have to expand a cubic or quartic on any evaluation. So we would have x cubed. And then if you guys recall that row in Pascal's triangle, 1, 3, 3, 1, we'll have 3, and then take one exponent from x and add 1 to h, and then take another from x and add 1 to h, so 3x h squared, and then 1 times h cubed. That's x plus h all cubed. And then we're going to have, we have our plus 1, and then we have minus x cubed, and also minus 1. Why minus 1? Because we're subtracting that polynomial, x cubed plus 1. all over h. I'm going to need to go into the right-hand side of my page for sure. But see, look, the same things keep happening. The stuff without an h divides out. 1 minus cancels out. 1 minus 1 is 0. X cubed minus x cubed is 0. Can I give you guys a tip? Let's say you forgot to subtract this whole polynomial, and let's say you have plus 1 here. And then when you're doing your simplifying, you have a whole bunch of stuff, and you have plus 2. And that plus 2 doesn't have an h in it. And you're just like, oh, well, I'll just cancel stuff anyway. No, all the h stuff has to go away. It's like a self-check. And if it doesn't happen, then you can go back and catch an error. Or if you're on a test, you can just fudge it, and hopefully your teacher misses it, or you just get more par marks. But anyway, I digress. Let's continue simplifying. I'll go up here. So we have the limits as h approaches 0. So what's canceling out? X cubed minus x cubed plus 1 and minus 1 are all gone. We're left with 3x squared h plus 3x h squared plus h cubed. Just those three terms, I think, right? All over h. Life is good. Everything there has an h in it. And I think for just managing space, I think it's reasonable I'm just going to divide out an h from everything. Just going to divide out an h from everything. Just reduces the powers of h on every single thing. We'll get the limit as h approaches 0. So what are we left with? 3x squared plus 3xh plus h squared. Nothing wrong with plugging h equals 0 into here. Now, if you guys are okay, you guys are all smart kids. So, sorry, you're not kids anymore. You guys are all smart. You're not young adults either. I don't know what to call you. You guys are all smart. I think you guys can all recognize when you plug in h equals 0, that is gone, that is gone. We're going to have 3x squared, right? So I'm just going to write down 3x squared. If you want to plug in and show that work, that's fine. It's just I know these calculations can start to get a little cumbersome. So show as much steps as you need to feel comfortable, but hopefully we're okay. That just simplifies to 3x squared. We've got another derivative in the books. You guys are doing great. That's 3 derivatives. Just to give you guys another tease to where we're going, and there's probably some of you guys right now who can actually start seeing some kind of rules develop, but in a couple days' time, we're going to develop some rules where we could go right from x cubed plus 3 to 3x squared in just seconds. But we do need to do a bit of this first just to get good. Yep. Yep. All right. You guys are doing great. We're doing lots together. I would like to do this one with you guys. You guys have done difference quotient for radicals before, but it can be a bit more challenging when there's an extra variable hidden here. So I'm going to do it with you guys. BA. What are we doing here? Are we doing B or are we doing A? We're doing B. I am 99% sure I will not fix that for the next time I give this lesson, but you never know. All right, let's give this one a try. Let's set up the difference quotient. Now, if you just want to blast ahead and give this a go on your own, I would love that. But I am going to do this one with you guys, and then I'll release responsibility to you guys, and you guys can practice. All right, I'm going to write out the definition. And then I'm going to plug in my stuff. So my function here is 2 over x. F at x plus h would therefore be 2 over x plus h. And then f at x, I'm subtracting, minus 2 over x. And now here's where this is my personal preference. I would rather myself, instead of dividing by h, I would rather write off to the right times 1 over h. To me, it just saves space and it looks cleaner. If you want to write everything over h, then you can do that. There's nothing wrong with that. It doesn't work for me, so that's why I write times 1 over h to the side. But as you guys know, I'm not your dad, so you can do what you want. The way we're proceeding here, like you guys have done a couple of these, we have to add, or at least in this case, subtract those rational expressions together. Not everybody likes doing this in grade 11. You guys actually only spend, I spent 2 days last semester with my grade 11s working on this skill. And then you kind of don't use it much, if at all, until this point in your math careers. So I'll do this one with you guys. But it is a skill that we've learned and we need to have in the toolbox. But we need a common denominator. So let's forge ahead. Just like when you guys were in grade school and you were looking for common denominators, one way to get a common denominator that works every time is to just multiply the denominators together. So we're going to do that here. We're going to write each of these rational expressions as a fraction with a denominator of x times x plus h. We took the first one and we multiplied the bottom by x, so we multiplied the top by x. And we took the second one and we multiplied the bottom by x plus h, so we need to multiply the top by x plus h as well. We still have our times 1 over h on the side. I can tell you for a fact that my 3U kids hated this and did not do well at this, so I can't wait to teach them calculus. But most of you guys can see where this is going, right? We always want this h on the bottom to cancel, and you guys can look ahead. Look ahead. We're going to have 2x minus 2x, right? That stuff's gone. We're going to be just left with minus 2h on top. H and the h will divide out, and then we can plug in h equals 0. Even though these algebra skills we're drawing on are, we're really stretching ourselves, it's the same patterns all the time. We want the h's to divide out. So I'm going to go move my face, and I'm going to go up into the top right here and continue. So what are we left with? So we have the limit as h approaches 0. Now that we have a common denominator, we can combine those two expressions. And look, we're going to have 2x. I'm going to do this to save some space. And just let's digest this, and you guys let me know if you want me to go over this again. But we're gonna have 2x, and then when we distribute the 2, we're going to have subtract 2x. Those will go away. We're also going to have minus 2h. Why minus 2h? Because we're subtracting that second expression. So all that's left on the top is minus 2h. We have our common denominator, x times x plus h. And then off to the side, we're dividing by h, or multiplying by 1 over h. So I just did a couple things at once there to manage my space. But common themes, look, h divided by h. See you later. And what we are left with is something we have no issue plugging 0 into. We have minus 2 over x times x plus h. There's nothing wrong with plugging 0 into that. And when we do, you get minus 2. On the bottom, you'll have x, you'll have x, you'll have minus 2 over x squared. We have found the derivative of 2 over x. So now at this point, we've got maybe 3 polynomials we've done the derivatives for. And you guys have done great today. This was some heavy lifting in terms of algebra today, for sure. We've done, I think, 3 polynomials going back to the motivation problem. We've done 2. You'll do a third one in a second. We've done the radical function, and we've done the rational function. These are all the types of derivatives that you guys need to be able to do according to our curriculum from first principles. It's now just time to practice. Here's one more for you guys to do. And this one, I will let you guys try this one on your own to start. I will catch up and I won't leave you hanging. I will do it too, but I want you guys to give this a go on your own. So one more polynomial. But those are the three types: polynomial, radical, and rational that we need to be able to do from first principles. We'll have tomorrow to practice, and then we'll learn on the next day. We have class, whenever that is. We'll start developing some rules to do this quickly. Yes? Sure. Yeah. And I've mentioned this too, but if you guys are practicing at home and you're doing derivatives from first principles and you're stuck, and like the worksheet I have for you guys next, I have full solutions posted. But like there is nothing wrong if you've at least tried going to ChatGPT, taking a screen capture of this function and saying, how do I find the derivative from first principles? I believe ChatGPT has no problem finding something like that. That's not cheating. That's actually smart, right? So it's okay to make use of those AI tools on your own when you guys are practicing. It's not cheating. That's just a good way to study and practice. You guys live in the golden age of taking math, where you guys can get help like that at your fingertips. No human being needed. All right, I'm going to pause the recording. If you're watching at home, I would give this one a try and unpause when you're ready to go. So Jackie, I think it might be helpful just to keep writing the definition of the derivative. I think this is going to be helpful for everybody, at least for a while. And that doesn't require you to have anything memorized. That's just the definition of the derivative. And then like just gives you that structure, and now you can plug in because you correctly had the expression for f at x plus h plus 3 times x plus h plus 1. And then we subtract f at x. And remember your grade 9 math, everybody. Subtracting polynomials. We'll put that second one in brackets. All over h. So that's the setup. And then I know I sound like a broken record, everybody, but that's because the same things will happen every time. You expand and simplify. Anything that doesn't have an h should go away and cancel. You'll then be able to divide out the h on the bottom, and then you'll be able to put in h equals 0. All right. So I'm gonna flex my math muscle here because I don't want to run out of space. So I'm gonna do x plus h squared, and then just double those terms. So that'd be 2x squared plus 2xh times 2, 4xh. And then h squared times 2 is 2h squared. And then I'll distribute the 3. It's a lot of terms to keep track of. Plus 1. And then don't forget we're subtracting all those terms from the last polynomial. Minus 2x squared minus 3x minus 1. Yeah, there is no sugarcoating it. We have to be good with our algebra skills from those earlier grades, for sure. All right. Does the non-h stuff wipe out? 2x squared minus 2x squared. 3x minus 3x. 1 minus 1. And then from what's left over, 4xh, 2h squared, and 3h. Everything has an h in it. You can divide them out. You're left with 4x plus 2h plus 3. And there's nothing wrong with plugging in h equals 0 into that. We would just be left with 4x plus 3. We have found the derivative of 2x squared plus 3x plus 1. So I am going to pause the video here. I think everybody I think we'll save number 2 as an exercise for tomorrow. I'll be right with you, okay? I'll come to see you. We'll save the back as an exercise for tomorrow. I'm going to give you guys some practice, and then we'll talk about our next steps here. So I'm going to end the video.